Hi, everybody. I am Gianluca Chiozzi, and I'm here for the second software session. For the ones who were not in the first session yesterday, I am from ESO, and I am chairing this conference together with Timo Korhonen. I just want to remind you a little bit about the rules of the conference, of the presentation. So please stay within your allotted time of 12 minutes plus 3 minutes of discussion. And we will inform you after 10 minutes that you have still a couple of minutes. For the audience, please keep your microphone muted at all times. And when you want to ask a question, raise your hand in the Zoom application, or even better, write your question into the VOVA question and answer. And then we will read your question, or we will give you the possibility of opening video and microphone. And okay, call the technical staff via the chat if you have any problems. Now, the first presentation of today is a distributed caching at cloud scale with Apache Ignite for the C2MON framework from Tiago Marques Oliveira. He is from Portugal, and he is working at CERN as a DevOps software engineer in accelerator control. Please, you can take control of the screen. Do we have Tiago somewhere? I don't see you. Timo, did you get any message?
No, no, I have not got any messages. So, so what should we do? Do we go with the next talk then already?
Okay, we skip to the second one. Is
okay.
Samuel Nyarko there?
I'm here. Yes.
Okay, so Timo, you can go on introducing.
Okay, right. So sorry for the change of the schedule. We try to get back to the normal schedule later. But the next speaker is Samuel Nyarko Tum from South African Radio Observatory. Sorry if I didn't get it right. And he will be talking about implementing an event tracing solution with consistently formatted logs for the SKA telescope control system. So please go ahead. So you can share the screen and start.
Okay, can you see my screen?
Yes.
Right. And is my audio okay?
Yeah, I can hear you fine.
Okay. All right, thank you very much for the introduction. Hello, everyone. My name is Samuel, and I'll be talking about logging and tracing in the SK telescope control system. Right. Okay, so just a little bit of background. So consider this system of rotating gears. The system moves because the individual gears push against the nearest gear. For whatever reason they are rotating to achieve, whether they are rotating to move a clock or some machine, it is clear from this diagram that one gear failing may compromise the entire system. Now, finding that one gear could be trivial it will require no mean feat. All right, so now shifting gears a bit from this illustration. Now let's, for instance, let's look at a more computing illustration. If your application has stopped responding because, say, the server that was hosting it has failed completely, you don't need more than just surface level data to figure out what's wrong. You can monitor the server, determine that it has gone down, and infer very quickly that you need to bring it up again, and then your application will start working again. Now, for simple issues where surface level views correlate directly to internal states, monitoring may deliver the ultimate result. But in more complex situations, surface level data alone is not enough to lead to the root cause of the problem. So again, imagine you have an application that is not responding. Maybe the server that holds the application failed, but as soon as it failed, your orchestrator automatically moved the application to another server in the cluster. So the failed server in this case is not the cause of the application failing. It could be that there's a bug in the application itself, for example, like a memory leak. And this bug will eventually cause any server hosting it to fail. Right. So the point I'm trying to make here is that crossing the lines from being clueless as to what is happening in the application to understanding your system's internal states is a function of observability. And like all distributed systems, the SK control system also has also a distributed system that has the same a lot of moving parts, and it also has this observability problem. So in this talk, I will discuss the steps that we have taken to improve observability in the SK control system software. Okay, so still on some background. According to several texts, including what I've referenced here on the slide, full observability of a distributed system is a function of three pillars. You have logs, metrics, tracing, can read the definitions for yourself. But then observability, as I've used earlier, generally defined means the ability to infer the internal state of a system from its external output. So this means that it's not just the ability to see what's going on in your systems, it's the ability to make sense of it all, to gather and analyze the information you need to prevent incidents from happening, and then to also trace their paths when they do happen, despite every safeguard, to make sure that they don't happen again. Right, so with background out of the way, let's go into some more specifics. Okay, so in our case, we are not building rotating gears, but instead we are building a telescope. More specifically, we are building an array of telescopes with a collecting size of 1 square kilometer. Now, this array, combined with the collection of devices, will enable us to observe some astronomical sources with much more deep exposure. One day highlighted more on this in his status talk yesterday. If you didn't see it, you can have a look later on. But the diagram on the left is just a trivial example of observing system, a telescope, and some devices. But there are a lot more devices that work together to give us our own observing telescope, like correlators, digitizers, even weather stations, receivers, etc. Now, on the right, this is not necessarily a representation of the entire SK control system architecture. The actual SK control system software is a collection of software and services which are maintained by at least 17 agile teams or more for both mid and low telescopes. And all these software and services are orchestrated in a Kubernetes environment. The diagram on the right is a hierarchy of Tango devices, demonstrating the control of the mid telescopes. Now, for those of you who don't know what Tango is, just something small about. So Tango device is just an abstraction of, like in this case, it's an abstraction hierarchy that has a functional purpose at the top and goes down to the physical form at the bottom. You can see in this diagram that there are some components that have some multiple instances over here, like here in the dish, the subarray, and the others that have like multiple instances here. So because of the many moving parts working together as a whole, the failure of one component, just like we saw in the case of the rotating gears, is very critical to the health of the system. And well, failures are inevitable, For us, most of the code maintained by the separate teams are well tested to at least qualify their functional behavior. But those tests only give us the confidence to deploy our code, but not necessarily to guarantee bug-free or fault-free software. So for effective debugging, we need tools to be able to identify and resolve almost immediately all triggers which have a signature of a bug or deviation from the expected behavior of some components. And achieving this in monolithic applications is usually sufficient with logs, but for distributed systems, you need distributed tracing. You need distributed tracing, that is logging, monitoring, and tracing for full observability. Okay, so working towards our tracing solution, we sort of a three-step, so can summarize in these 3 steps. And so at the initial onset of the bridging phase, so again, yesterday one spoke about the bridging phase where we pulled resources from teams in the partner countries to start working on the software for the telescope control system software. So during this bridging phase, these teams came up with several packages, and these packages maintained by these teams had their own approaches to logging. So our first step was to harmonize logging approaches so that we have consistently formatted logs across all applications. And then we also provisioned a unique ID generator to be used as tags in the logs. And the first 2 are pretty much the scaffold. And with those ones in place, we then went on to build a transaction library that that provisions the context handler. And inside this context handler, we can emit SQL formatted logs with the transaction IDs injected in there. Okay. Right, now, just to discuss a bit more on what we accomplished in both the logging and making the unique ID generator and the log transactions library. So after did a bit of a survey in the packages that the teams had worked on at the time, we were working on this solution, and we proposed and implemented our own SQL log formats, which looks like what we have here on the screen. And there are some compulsory bits in this format. So the parts that are colored red are sort of compulsory. All logs have to have that. And there's a lot more detail as to what each section of the log is supposed to look like, and all that. The format of it, the details is inside our SQL developer portal. But the way we came by this, like I said, is we gathered from the preliminary results, we gathered from analyzing the code base of existing projects. And that drove our design of this card standard, referring to, in addition to that, we also referred to the syslog format. And then with those 2 married together, we build our own format from the ground up. And we had sort of like 3 main pillars that we were looking out for our log format. So we emphasize readability, sensible log length, and the ability to pass logs if you want to use things like Kibana or the ELK stack in general. Okay, so the log format is available in what we call the SQL logging configuration library. And this package allows the developers to configure logging for any module so that the modules log in a consistent format. And this is used across all teams in the SQL Agile streams. So to use the package, it's as simple as the snippet above. All the magic happens in the text colored highlighted in yellow here. And this function should be used to configure the application's logging system as early as possible to be able to have logs come out like the ones I believe over here. Okay, so
2 minutes.
Okay,
Sorry.
right. So we also have a unique ID generator. I won't say much about that, but that one has a remote and local ID generator. So hard pressed for time. This is the main catch here. So the ID generator and the login library fan into what used to be built called the SQL transactions library. And it just provides a context handler, which is, you can see here, which imports this transaction class. And as soon as you're in this context handler, a unique ID is generated, and that ID will be injected in all your logs. And the way the ID looks like, if you look at the note I have here, well, as soon as you enter the transaction, the context handler, you have this log spewed out. So you have transaction, the ID generated, the name of the events or command you're trying to execute, and some parameters follow. And there's a marker that tells you the start and end of a log of a trace. Okay, so this is how the logs look like. I'll just jump through that. You can have a look at it later. And for the curious, anyone who wants to go look more, we have an example sort of multi-device which shows the log transaction library in action. So at the top level, it talks to sub lower level devices. And right from when a command is issued at the top all the way down, the log is passed from top to the lower level devices, and that shows a trace. So that is available in another repository on the SK organization in GitLab. Okay, so this is my conclusion, and thank you for your attention.
All right, thank you, Samuel, for your talk. I see there's one question. Lana is asking, why do you start the log message with version and not this timestamp?
Well, as far as I can remember, there's no real reason why one keeps the order of the sections of the log, and that the version and the timestamp are all composed in the log that is spewed out. There wasn't a special reason why the version came before the timestamp. And also, if I cast my mind back to the syslog formats, I think the version comes first before the timestamp, but there wasn't like a real design reason why the version came before the timestamp. So thank you.
Right. Thank you. I don't see more questions at this moment, so maybe we can move on. Thank you, Samuel, again for your talk.
Okay, do we have Tiago now?
Yes,
Oh,
I'm
yes.
here.
Yeah, you are. Okay.
Yes.
So,
and sorry about the delay.
No problem. It is destiny of this conference that the first two presentations get switched, like it happened yesterday as well, because of my.
I was here.
phone.
Yes.
Yes. Please go on with your presentation. I introduced you already before.
So can you see my screen, my presentation?
Yeah.
Yep.
Okay. So hello everyone. My name is Tiago Oliveira, and I'll be presenting a distributed caching at cloud scale with Apache Ignite for the C2MON framework. So in this presentation, I will start for briefly introducing C2MON. Then we'll go over to see the differences between a traditional cache versus a distributed cache and see how this works, and finalize with the integration with Apache Ignite. So starting with the introduction to C2MON. So just to give a bit of context, at CERN, we have more than 267,000 endpoints that can come from different sources, as you can see from the images, like the computing center, QPS, which stands for Quench Protection System, cooling, ventilation, and others. And all of these needs to be controlled on the CERN control center. And so for that, C2MON was created. So C2MON stands for CERN Control and Monitoring Platform, and it's actually an open source platform. So if you're interested, you can check it out through this website here. And it's used for industrial controls, data acquisition and monitoring, and it provides a high availability and fault tolerance. So it makes it a perfect fit to handle all of these complex and critical systems that are present at CERN. So how does C2MON gather all this data? So for that, C2MON uses a data acquisition API, which collects the data from all the different sources and sends it to the C2MON server tier. and the number of messages can reach up to a few millions per day. So C2MON needs to process all of them while maintaining data consistency. And this processing can include the evaluation of tag values, activation or termination of alarms, rule calculations, and others. And so to maintain this data consistency, C2MON uses a classic client-server cache with a distributed cluster, and in this case, Apache Ignite, which not only helps with the scalability and consistency of C2MON, but also takes part in the possibility of having rolling upgrades. So if we decide to run multiple instances, like we see in the image. So if you wanted to upgrade just one node, the other would keep running, so this would be transparent for the client. So now let's take a look at the differences between a traditional cache versus a distributed cache. So usually on a more traditional cache, the cache runs embedded with the application on a single instance, whereas on a distributed cache, this is external to the application and it has its data spread out across the several nodes on a cluster. So how do these distributed caches work? So in the next slides, I will show a bit of these cache operations with a distributed cache. So for this simple example, we'll start with our app, and instead of explaining all the different nodes, we'll start with just one to simplify. So each node is composed by three main components. So we have the logical storage, which basically represents all the data that's available on the cluster. So not necessarily on this node, but data that can be fetched from other nodes. And on our primary storage, we have the most recent version of data that was inserted. And for example, on Ignite uses an off-heap memory to allocate memory regions outside of the Java heap. So the data is not subjected to garbage collection, making the information more predictable. Finally, we have the backup storage, and this contains a replica of data that was inserted on another node. And this is for failover purposes that I'm going to explain on the next few slides. And to simplify on this example, I will show in an embedded distributed cache. So the app and the cache node will run on the same JVM. So let's start with 4 different nodes. And in this example, the nodes join each other on the grid through node discovery mechanisms. And so we're gonna start with an example data called C. As you can see, data C is available on all the different nodes on the cluster, and it's stored here on JVM3. But let's say we want to add a new type of data called A. The first thing you're gonna see is that the data is gonna be available on all the different nodes as it's inserted on JVM1. Also, a new backup is created on a different node. And as I explained before, this is for failover purposes. So if we lose our node 1, or if the node is killed, we don't lose completely our data because it's stored here as a backup. So if our data is very critical, we can increase this number of backups to reduce the chance of losing completely our data. And the only downside is that it decreases the performance of cache operations. So finally, we're gonna see how to update this data C. So data C already exists in our cluster. So the only thing we need to do is to update our primary storage and our backup just to maintain consistency of data across the cluster. So let's add a bit more data. And now we have 4 types, A, B, C, and D, and we want to retrieve them all. And in this example, each piece of data is managed by only one node in the cluster. So data A on the primary storage of JVM1, data B of JVM2, and so on. So this will require just one single hop. And this is extremely scalable because it takes a great advantage of all the nodes in the switched network. So what if we lose one of our nodes, as we said before? How does the distributed cache handle failover? So let's say we lose our node 2, and node 2 contains data B as its primary storage, which also resides as a backup on JVM3. So the first step is to promote this data as primary storage and to create a new backup on JVM4. The same goes for data D, which backup was lost when the node was died or was killed. So a new backup is created here also on JVM3. And now if we wanted to retrieve again all our data on the app, this would be transparent because as we have backups, no data was lost, so the app doesn't even know that one node died or was killed. So what are the main differences? So first of all, we have scalability. So on a distributed caching architecture, this can easily scale horizontally just by adding new nodes to the cluster, whereas on a more traditional caching architecture, it only supports vertical scaling. In terms of redundancy, as we've seen before, a distributed cache, we have redundancy, which doesn't occur on a single instance caching. And finally, in terms of reliability, usually traditional caches use the same heap space as the application, so there are constraints of memory, whereas on a distributed cache, it runs independent processes across multiple nodes in a cluster, so it's transparent for the program if one node dies or is killed. So now that we saw the differences between a traditional cache and a distributed cache, let's now take a look at Apache Ignite, which is an implementation of a distributed cache. So Apache Ignite is an open source distributed database and computing platform, and it provides a simple interface to work with large amounts of data, and it's written in pure Java based on Spring. So what were the main steps to help this integration in C2MON? The first of all, we have the creation of simple and serializable and stable domain objects. And this was to avoid breaking changes because C2MON is a 24/7, 365 days critical system that needs to always be running. And so it's difficult to update these domain objects every time. And furthermore, this would kill the possibility of having rolling upgrades. And for C2MON, this means having equipments, data tags, alarms, and others. So the use of generics was also very important, as you can see here, called cacheable. And this was to restrict what types of objects could be persisted and to avoid the possibility of having inconsistencies in Ignite in the future. And finally, Spring proved to be also very useful when interacting with Apache Ignite, because we can easily set it up with beans and configure it with the Spring Boot configuration. And still on the context of Spring, the transactional annotations, as you can see here in this example, is very useful because Ignite creates a transaction around the method, and so we can wrap a number of actions that should be executed as one unit. So I also mentioned cloud in the title, and that comes from the way that C2MON is deployed. So although Apache Ignite is a cloud-ready application, C2MON is not there yet, and so it's impossible to take fully advantage of all the capabilities of Ignite. And the solution is to use orchestration, which would greatly increase the speed of deployments and reconfiguration of C2MON. With this, we would have also the possibility of doing rolling upgrades, like I showed before. We could just upgrade one node of C2MON while the others maintained running, so this would be transparent. We'd also achieve load balancing and also scalability. Regarding this orchestration, I would invite you to also assist to the presentation of Rémi Voirin the next Thursday, the 21st, regarding the state of containerization in CERN accelerator controls. So let's just have an overview of what I showed you in this presentation. So we saw that C2MON is a critical piece of infrastructure which needs to run 24/7, 365 days a year. Scalability, consistency of data, and rolling upgrades are crucial. And we saw also that a distributed cache like Ignite is a good solution to achieve those goals. Finally, we saw that the integration of Apache Ignite with Spring made it easier to set it up and configure, and that with orchestration and Ignite, we have the way paved to move to the cloud. So thank you very much for your attention, and I hope this presentation was useful.
Great, very interesting and absolutely perfectly in time. I see that we have one question. The question says, seems it is a little like a data broker like Apache Kafka, what is the difference between them? I notice and2com is based on Apache Ignite.
Yeah, so C2MON uses a lot of not Apache Kafka, but a lot of brokers with active MQ. And so the concept is a bit different because what we use a lot is instead of queues with topics. And yeah, there's a bit of a difference there. But it would also be very interesting if we could maybe integrate Apache Kafka on C2MON, because I also used it before and I know it has a lot of advantages. So thank you for your question. Yeah.
And there is another question here. The exchange of data between nodes requires a very performant network communication. Do you have issues with communications?
Well, as I said before, right now, the way that C2MON is deployed in production, it's not fully able to use all the capabilities of Ignite. But with our tests, we actually used Kubernetes, and for now, I think it's just a matter of tuning a bit the configuration, because, for example, as I said before, if we have a big number of backups, this could highly decrease the performance of cache operations, so that might be one issue. But other than that, I still had any problems. So.
Okay, I see also Rafael Muller has raised his hand. Now you can unmute and ask your question, Rafael.
Sorry, that was a mistake.
Oh, okay, good. Then if there are no other questions, I think we can move to the next presentation. Many thanks, Tiago.
Thank you. Thanks a lot.
Timo?
Okay. All right. All right. The next then would be Piotr Goril from S2 Innovation, Krakow, and he will talk about Tango controls RFCs. So please go ahead, Piotr.
Good afternoon, good morning, and good evening, to all the world. I'm the honor of speaking on behalf of the Tango community about the project Tango RFCs, which is a documentation of the already existing control system framework. Why we do this? Of course, the Tango controls is mostly used for scientific projects, and the scientific laboratories do cutting-edge science, and then they need changes in time. So the technology they use, it's also changing, and then Tango controls also adopt to this to follow the needs of the scientific community. And it's worth to know where we go on one hand, and on the other hand, it's also worth to be able to steer our travel. And then the Tango for Tango control is a framework. It's written, it has the modules written in C++, in Java, in Python, and even in Rust. And then each of these is going on their own, also all the waves of their technologies, and they go, of course, in the same direction. But the waters we save are not all, the waters we navigate are not always very safe. So there are bugs to be solved and could possibly also change the direction of each of the ship. But also there are the libraries, operating systems, and the compilers we use, and that get old. And then also the first developers who knows details of the implementation of the libraries go for retirement, so the knowledge disappear. And then this makes maintenance and features implementation sensitive to losing the compatibility and so on. So after 20 years of evolution of Tango controls, the Tango community decide to make the precise documentation of what Tango control protocol is. So to map the Tango world, to be able to navigate it, maybe even to go to the sky. So they decide to write the formal documentation. But the idea behind the RFCs is not to document the code. So it is not to document the code, but because the code is now this kind of specification of the protocol. It is to make the formal specification of the already existing concepts, terminology, precise description of the behavior and the convention used. And this should provide the map that will allow the community to easily navigate during the maintenance of the existing libraries, but also so to be able to safely go to the edge of the map and then make the maps of new areas. And of course, as for all the journeys, there's the most important part is the crew, so the team that is going to the journey, and then for the for the Tango RFCs, the team was built from the volunteers from the whole community. So to keep all the knowledge of all the understanding of the Tango that exists in the community, in the collaboration, these teams meet every 2 weeks to synchronize their work, to synchronize the process. There was also the leading role of the student innovation company who were chairing the meetings and do administration work. But the most important is that there was quite a lot of people involved. They spent a lot of their time, sometimes even after hours, to write the specification. And of course, we have a team. We need also the ship, so the tools. One of the most important tools that has been selected, it was suggested by Vincent Hardian from Max 4, is to use consensus-oriented specification systems. It's a similar methodology that is used by Protobuf or by ZeroMQ. As we are mostly developers, so the work was conducted with use of Git to track the changes. Documents written in text formats, markdown using the IBNF, so augmented Backus notation, for precise descriptions of the communication tokens. We use Slack for discussions, and also we use remote workshops, right? The RFC workshops that were very important for boosting the development of the RFCs. And of course, most of you know what the RFC is, but some of you may wonder. So RFC stands for a request for comments. So the idea of RFCs emerged in the beginning of internet in the United States, the Agency for Advanced Research, where the researchers that were working on the first internet protocols were circulating papers around the offices, and they comment each other and they get to some consensus. And out of this, a lot of specifications appears, like SMTP specification, and even there is a specification of the IP network built with use of pigeons in case there is a power failure in the world. So that's this kind of protocols are specified, and then the selected this COSS methodology has been selected by the community as it's compatible with RFCs. So it's basically the way how the RFCs appears. The COSS specifies the lifecycle of the documents, how to name the documents. For the details, you may refer to the paper and to the COSS web pages. But the most important feature of this methodology is that it facilitates collaborative work. So it's not that someone, for example, for the student innovation propose something and say, okay, it's their specification. No, it requires, the process assures that the things that get as to specification is something that is really interesting and needed by the community. We use C4, that stands for collective code construction contract, which is methodology similar to Git flow. So because we are the software developers, so we use Git to send merge requests with new parts of the specification. And there's an editor appointed by the Tango collaboration who makes sure that it's what we deliver is really what is needed by the collaboration, by the Tango community. And just to summarize, we use Markdown, ABNF, and UML. We meet regularly to keep pace of the work. Now we suffer from the last mile effect, but the work is usually bossed with the workshop. So this is also quite important experience we get, that workshops, so the time we sit together, even in the different locations, but working on the same thing, really boosts the work. And then at the beginning of the work, we defined the map, the world of the Tango controls into several charts. As you can see here, it is more than 21 charts proposed. In fact, to start development with, for example, new Tango V10, we can use we need only 13 out of them. As you can see, some of them are already green. It means that they are the so-called draft mode. Draft mode is that they are ready to be used as a base for prototyping. And after the prototyping prove its completeness, it will go into the state of stable. And then the results are the documents rendered on the read the docs as a part of the official Tango controls documentation. So the documentation was already there, but those documents were never not so formal, and the RFCs are very formal. They use ABNF for specifying the information exchange formats, but they also use a very strict way of verbing the wording the sentences that are very like we use like must or shall or is recommended to point out what's the value of the certain rules in the specification. Okay, I already mentioned V10 versions. So in fact, what we have documented, we documented current state of the Tango, so Tango V10. And then we plan to use these RFCs to develop Tango V10, which will be V10 features in the new shape. And then later also to evolve the specification to V11. So you may imagine that now Tango V9 is like Challenger. V10 will be like new spacecraft that will have the same feature of the as V9, so it will be able to go to Earth orbit. And then V11 will be could be completely new spacecraft serving the same purpose, but would be able to go beyond the Earth orbit or solar systems to discover new galaxies. So this is how we think that, and we know that this COSS process will allow also go to V11 and even V12 for the future. So we did, of course, this for purpose. So there are some of measured benefits of writing RFCs. One is we expect it will allow us to manage the future of the Tango controls. And there are some very, very important additional benefits or side benefits, like the community tightening. Since quite a lot of us were working together, we also get know each other better, and we build the terminology consistency. So everyone who knows something about philosophy, they know that one of the most important parts of communication in the philosophy is to have the same meaning for the same words. And we built this approach, or we improved this a lot in the Tango community. And then during making the RFCs, we spent quite a lot of time of reviewing the current source code. So the knowledge has been already gained and shared how the source code is built. So there's more developers who can deal with kernel of the Tango controls. We already discovered some features that are already implemented, rarely used, but we discovered such things. Also, we discovered some additional bugs that could be solved. And there were a lot of discussions about the future of the Tango and about the improvement of the current code base.
Okay.
So thank you very much for your attention. And also thank you the Tango collaboration for making this work happen, for the financing the work, and also for spending the time and on working together. Hope we will follow the work in the future. Thank you very much.
Okay, thank you, Piotr. Perfectly on time. So, and we have some time for questions. Are there any? If I don't see any in the chats, but I have one which maybe a bit take long to answer. But when you have these RFCs, what is the process to decide which ones you put a priority on and go into development? So there was a discussion, of course, in the community, but the process is the way that everyone can start. We have the list, can start any of the document. If he has some ideas for the document like RFC 15, he write and send a merge request. Then is of course capability of Tango collaboration to appoint or someone from the Tango collaboration core institutes to become the editor of the document. But usually it is quite fine, and to find the time to review. So I would say we decided, of course, on some priorities, but in fact, the first documents were like command, device servers, and then the most important one, like request reply protocol, is now still in the progress. So it was
because everyone finds it maybe it will need requires a lot of discussion and so on. So it was left for the later, and we still like now at 80% of this specification on the way to make it draft.
All right, thank you.
Thank you very much.
Victor, again. I think we can now should move to the next speaker.
Yes, the next speaker is Matteo Di Carlo from the INAF in Italy and working at SKA since 2015. He will talk of continuous integration, continuous development practices at SKA. Matteo, to use the screen.
Hello, everybody. I hope you can hear me and you can see my screen. In case, tell me. Today, I'm going to talk on behalf of the SKA system team. And so this is not only my work, but it's a work of an entire team. So if you don't know, the SKA project is an international effort that in order to build 2 radio telescopes, one in South Africa and one in Australia, there will be one observatory monitoring and control from a global headquarters based in United Kingdom at Jodrell Bank. The software development process selected is agile, which is mainly incremental and iterative. And we are many teams at the moment, 9 teams. This number is growing, including one specialized team known as system team devoted to continuous integration, test automation, and continuous deployment. So why we need the CI/CD? So in the context of SKA, there are many parts of the project developed independently, and normally this work go for weeks or sometimes longer. So when you integrate together with all the parts together, it is possible that the code base and the build environment diverge. This is known as in literature as integration hell. What does it mean? When the changes are integrated, developer can spend time in solving bugs that are probably introduced weeks earlier. So to avoid this problem, we have to establish a culture, which is basically a set of development practice that require the developer to integrate the code several times a day. And each check-in, each commit is then verified by automatic build, and the team can detect problem as early as possible. So when we say continuous integration, we normally refer to a paper written by Martin Fowler back in 2006. The theory is pretty easy. We must have one single source of repository. We shouldn't use the branching. We should automate the build, the testing. Every commit should build into another machine. We should commit often, and clearly the smaller is the change, the easier is the fix. We should build fast, and possibly we have multi-stage deployment. Now, this is the theory, and it is not always possible to implement it. So I'm going to present basically the practice that we adopted in SKA. The continuous delivery means that basically we want to automate the delivery of new software releases. This means that the deployment must be predictable and sustainable. The code must be in a deployable state, and testing is an important part which needs to cover enough of our code base. The continuous deployment goes one step further, meaning that every commit that passes all the build and test pipeline, and then it is deployed into a production environment. Since the beginning of the SKA experience, we have seen it the right path as the containerization. So the SKA project is basically have been divided into a set of elements. Each of them is composed by a set of software modules. Now, for each module, there is one repository, and for each repository, we decided that there must be at least one container image. Why a container? Let's say that it's very convenient to package up an application in this way, because, for example, if we have a dependency, we can solve it inside the container, in a layer in a container, once for all. So this is an example of a containerized environment. one of our dependency is the Tango control. So in this project, the SKA Tango images, we basically have put all the library for the Tango control framework inside a set of Docker images. And at the end of the day, all the developer must do is to extend one image from this hierarchy. Please note that this is only a partial set of the container image that we have in this repository, since we are basically moving from Debian to Alpine. So since we want to go for container, we need an orchestrator, and the choice for the container orchestration went to Kubernetes. In Kubernetes, you can define a microservice architecture. In our world, a service can be seen as a Tango control server or device server. We also use Helm for packages those applications. Helm is basically a tool for managing Kubernetes chart, where a chart is basically all I need to deploy an application. An important decision is that for each SKA element, there must be an Helm chart for installing it into Kubernetes. And we make use a lot of Makefile for lifecycle management. Basically, there is a target for everything, for building image, for testing, for cleaning, and so on and so forth. Helm has an important concept of the dependency. So basically, it is possible to have a chart which is dependent of another chart, so to resemble a hierarchy. So the integration in our case can be done with this concept, but we have to consider the operational aspect of this. So basically, even if we can have a very big hierarchy, at the end of the day, everything is going to be flat for Kubernetes. So we decided to go for umbrella chart. So basically, instead of having a big hierarchy, we have an umbrella which contains all the chart we need. And clearly, this allows us to have a subset of umbrella chart for integration purposes. So basically, for every SKA element, we have at least one umbrella chart for integration testing. Another important tool we selected is GitLab. GitLab is basically a DevOps lifecycle tool, which provides a number of features. The most important one is the continuous integration deployment pipeline. So in this diagram, basically we show the GitLab model. In every Git revision, there could be a pipeline configuration, and when you commit into the GitLab repository, we have a number of execution of a pipeline. A pipeline is basically composed by a number of jobs, for example, building, linting, testing, or publish artifact, which can happen or can deploy things in an environment. Clearly for us, the environment is a Kubernetes cluster. Another important thing to notice is that testing is divided in two types. We have pre-deployment tests, let's say with mocks, and also post-deployment tests, which happen with the real application. So basically we install the chart, we test the chart, and then we uninstall it. At runtime, what is going to happen is that when a developer commit, it triggers a pod, a container in an isolated Kubernetes namespace, which can create other namespace which are isolated. Clearly, we have a number of other features, for example, our artifact repository, or Prometheus for monitoring, Elasticsearch for logging, and Ceph for storage. This is just an example pipeline to show one important thing. Although we have a number of feature failure in every repository, what is important is that the master branch is always deployable, so it always works. And this is exactly what we expect from every repository in the SKA project. Taking a look at our infrastructure, we basically have one gateway. This is deployed in a cloud environment, okay? The gateway exposes basically a number of services like the VPN or the load balancer for the Kubernetes, the authorization through GitLab. We also have clearly the Kubernetes cluster, which has a connection to Ceph for storage management with Rock.io. We also have JournalBit in our worker for sending logs to the Elastic Stack, and then we have Prometheus for monitoring. We also have in our cloud the artifact repository as Nexus. So we have also an engineering data archive, which at the moment is MariaDB, and we also have an InfluxDB for other kind of metrics. if we take a look at the Kubernetes infrastructure, we can see that there are a number of masters. In our case, we have 3 masters which are elected basically for to avoid failure. And also there is a round-robin load balancer for internal and external access to the Kubernetes, and we also have fault tolerance for the internal database of Kubernetes. As you can see, the workers are there. At the moment, we have 9 workers. Each of them basically has to service the kubelet and the kube proxy. This is basically a standard or pretty standard deployment of Kubernetes. We also cover a number of quality aspects with basically 3 repositories or 3 projects, if you prefer. The first one is we call the CI automation. It's basically a web application with a plugin architecture which receive webhooks from various sources, for example, from the artifact repository Nexus, from GitLab, or other sources like Jira. When a webhook is received, a number of the plugin is activated, and for example, one of them trigger the validation for quality aspect. So what exactly this do? The Nexus webhook, for example, we have a new artifact that put a message in a Redis queue. When this Redis queue has the message, another framework, another project take this message and create a task to process the artifact. What we do, we basically check for metadata. Basically the Docker image has to have an author and a repository where it comes from. And also we activate the container scanning basically for vulnerability checks. Once a validation is done, we will put an entry into a database, and in case the artifact is not valid, we will quarantine it. Okay, the quarantine phase is basically moving the artifact from one repository to another that we call the quarantine artifact repository. So
you have 1 minute left. Okay.
I am at the conclusion. So basically, what is our practice, or what are our practice? So every component of our system has its own repository, and we use storage-based branching. So when you open a branch, the branch can be open for a maximum a couple of weeks. We make a large use of Makefile. There is a target for everything. Every commit trigger a pipeline in GitLab that build, lint, execute unit testing or pre-deployment testing, and integration testing, as we call it, post-deployment testing. Building is pretty fast at the moment. Usually it takes around 10 minutes. Depends, we have few exceptions. The integration testing happens in an isolated Kubernetes environment, so we don't have anymore the integration environment, the production environment, or staging environment. Everything is isolated. We create environment on the fly, and every artifact is checked for quality field and quality aspects. So thanks for your attention.
Thank you very much, Matteo. I see a couple of questions. The first question is from Carlos Pascualzarra. You use Makefiles for everything. Doesn't it overlap with the use of Helm charts? And also, doesn't it make less modular, more difficult to reuse?
So okay, that's a place where we are currently working. So the Makefile use Helm for basically deploying everything. We have a project for the Makefile, and basically in every repository we have a module for importing the Makefile. This will give us a standardized set of folder and a standardized set of targets. So basically this is the answer.
Okay, another question from Benjamin Peter. Who is creating the container images? How many variants are there? And how is the process if the container needs changes?
So the container is the pipeline, is the GitLab pipeline that create the container image, that build the container image. Initially, it push the image into the GitLab registry, and then when the post-deployment testing pass, we push into the Nexus artifact repository. We do not allow to overwrite the image, and we do not allow pushing from other sources from your local laptop. Basically, only the GitLab pipeline can basically push image into the Nexus.
Next question, do developers have access to Kubernetes dashboards to observe performance of the pods during running their applications?
The developer can access the Grafana dashboard, which will give you the performance of the pods from the Prometheus data source. So we don't deploy the Kubernetes dashboard, what comes for free with Kubernetes, but we have a set of dashboard for Grafana, and the developer are must check those performance parameter.
Okay, a last one. I'm actually putting together two. How many developers are contributing to the code base, and how many people are involved with the setup and maintenance of the overall DevOps infrastructure?
So concerning the second question, how many people are involved in the DevOps infrastructure? It's the system team. So we are around 7-8 people. The code base, the developer contribute to the code base are much bigger. So basically we are 19 team, around 150 people or developer. This number are growing anyway.
Okay, thank you very much, Matteo.
Thank you for the questions.
All right. Okay, then it is time for the final talk of this session. So, and the speaker will be Davide Marcato from INFN, Italy, and he will be speaking about PyAssembly, the Python finite state machine library for epics. Do we have Davide? All right, there we go. Okay, please go ahead.
Hello. Okay, can you hear me?
Yeah. Yes, please go ahead.
Okay, one moment. Okay. So I will present the PyAssembly, a Python finite state machine library for epics. So in the epics community, the sequencer is the standard tool to define procedures and sequences of operations. It was first proposed in the original epics paper, and this tool has good performances and high reliability, and it has a good and flexible programming model. It is based on the state notation language, which is a C-like language, which is then transcompiled to C, and it's used to describe finite state machines, states, and transitions. But this tool has it uses a low-level language, which is unfamiliar to new users. It's hard to expand it with different with other libraries, and it's not always easy to read. Are there alternatives? Well, one could use directly PyEpics script, where PyEpics is a library to which wraps the channel access epics library. And this is easy and fast to prototype, but it has very basic functionalities for finite state machines. One can only read and write from the channel access. Then there are other big projects, like I mentioned the Blue Sky project, which is a complete suite of tools for data acquisition, experimental specification, and orchestration, which has advanced functionalities, but it requires a big investment into the design model of the software. I'm sure there are other specific tools which are specific for a certain facility or experiment, but they are not widely available or widely known. And so I here presenting PyAssembly, which is a simpler alternative to the epics sequencer. This lets you describe a finite state machine at a high level, leaving the implementation details to the library, and it's built on PyEpics, on top of PyEpics. The usage of the Python language is important because this is a high-level language, and a lot of new users are familiar with it. And so this offers a lower barrier to entry. And also there is a rich and scientific and engineering ecosystem of libraries, which can be integrated with this library. So let's see how this works. So this is a complete example of a finite state machine, which can be run like this. And so you see that apart from importing the library, you just derive from a class which is called SM base. Then on the constructor, you connect to the PV, to the process variables with their name, and you specify the first state to execute. Then the states are defined as methods of the class that you're defining. For example, the idle state here is defined with the idle eval method, where you simply wait for a rising edge on the enable PV. And then in that case, you change state to mirroring. In the mirroring state, you check the falling edge on the enable PV. And in that case, you go back to idle. Otherwise, when the value of the counter PV changes, you read this value and you write it on the mirror PV. So in the mirror PV value will always follows the counter PV. So this is just a simple example. This is the schema of this simple finite state machine. But it's to demonstrate that with just 30 lines of code, I can write a finite state machine without any details without any low-level details. Then there is a loader which helps us loading the finite state machine and executing it. So the design goals of this library is that a finite state machine should be event-driven. So we don't want to do polling. We chose a daemon-like execution flow. So the finite state machine is always running in the background, waiting for an enable signal to start its core operation. And we choose to have a concurrent execution of multiple finite state machines in different threads on a single process to maximize network efficiency, so that all the finite state machines in the same process can share the channel access connection to the PVs in order to maximize exactly the network efficiency. Also, we don't want that the inputs change during state execution, and so we made a caching effort in this way. And also each input must trigger one state execution and only one. We also have the ability to run actions on state transition using the entry, eval, and exit methods, which we will see now. These are the main classes of the library, which can be divided into input management classes, FSM execution, timers, and other utilities. So let's see the input management. Okay, the channel access defines three types of events. There is the change event, connection events, and put complete event. So at the beginning, one PV emits this event, and the event data is recorded and placed on some thread safe queues, one for each thread of the finite state machines loaded. Now these threads are waken up so that they can read the data from the queues. And now with this data, they update FSM.io instance, which is a local copy of all the inputs to which the finite state machine is connected. So by using this local copy, we are guaranteed that the input does not change during the state execution. The local copy is updated only before the current execution with the data retrieved from the queue. And finally, the current state is executed, and we can use the trigger event type to check on edge conditions. For example, we can say that a value is rising if the event type is changed and the new value is bigger than the previous one. The execution flow is divided into three methods for each state. So for example, for the example state, we can define the example state underscore entry method, which is executed only once during the transition to this state. Then the underscore eval method is executed every time a new event from the channel access arrives, and the code of the user should check what to do. And then when required, it can call go to state, which changes the state of the finite state machine. And so an exit transition is executed, and then the underscore exit method is automatically executed just once. And then you go back to the first step with the new current state. The go-to-state method automatically finds the right method based on the state name, with and then it looks for entry and eval and exit methods. This is a complete example of a change event, and you can see that the PyEpics library calls our callback, which puts the data on a queue and triggers all the FSM execution. These get the data from the queue. They update with the resetted updated. They update the local copy of the of an input, and then the current state is executed with the 3 methods. And the user code, which is here, can read the current value or the edge conditions of the inputs with the methods of the FSM. Then there are timers, and timers are used to wake up the FSM after a fixed time delay. And this can be used to perform, like to check timeouts, to perform periodic actions, so just to wait before an action. These are implemented using an internal event of type timer expired. And there is a thread which manages all the timers. And you can see here, the user can set the timer, give him a name and a timeout, and then check on the method if it's expired with the name. There are other utilities like a logger, which offers a unified interface to log different backends and to log 2 different backends. Also a loader to load the multiple finite state machine on a single executable and shared resources, and the watchdog mechanism where you can specify a PV as watchdog. And there is a thread which periodically writes a value to this PV, which can be specified, of course. And you should build the PV so that it goes into alarm if no writes occur after a certain delay. So this library was first developed in 2016 for the RF control system at Legnaro National Laboratories, here where I work. And now it's used for many other subsystems like diagnostic, ion beam sources, vacuum, and others. We also use it to build simulators where you can replace real hardware devices by simulating their actions on PV. This is used to test the software. Or for alarm handling, for example, I have a script, a simple Python program which sends a notification via Telegram using the Telegram bot API, and this was released to implement with this library. Also, we used it for beam dynamic optimization procedures for the Polina project. In general, this is useful when asynchronous interaction is expected. For example, a user that in the user interface clicks a button and expects something to happen, or where there are non-constant delays. And this is the important part is being able to act on rising or falling edges of conditions. Then the library has been published. It's available on GitHub. And this is the link. It has a GPL license. It's available on pip, so it can easily be installed with a command. And there is online documentation web-based. So concluding, I've presented the PyAssembly, a library to develop EPICS finite state machines with a focus on simplicity. It offers great expandability with Python, with many Python libraries. And it has a lot of useful features for common use cases. It's available to the whole EPICS community because it makes no assumption on your environment. You just, if you're using EPICS, you can use it, and there are no other requirements, or Python, let's say, but of course. And it's tested and running in production here at Legnaro. For future improvements, I would like to add support for different input types. For example, currently it does not support PV access because we have no experience with this protocol, but of course, contributions are welcome. Thank you.
Right. Thank you, Davide. Would have time for questions, I don't see any in. Let me check. Oh yes, there is one. You write Python with threads. Did you consider to use Python async IO instead?
Sorry, I did not understand. I wrote Python with
threads, using execution threads.
threads. Yes. No,
yes,
no,
right.
I did not consider it because well, I don't know them, so I'm sorry, but I did not know about them.
All right. Okay, so if there are no more questions, then thank you, Davide, again for the
Thank
talk.
you.
And this concludes our session today. I think I missed one question in the session Q&A earlier, so I would encourage all speakers to take a look if there are new questions in the Q&A, and maybe write reply to the Q&A.
Yes, I also want to thank you, all the participants. I think that that this session was particularly good, interesting, with a lot of questions, and this gives me a good feeling about the conference. I hope you all enjoyed it, and any questions, discussions, and so on can go on in the chat of the sessions. So thank you very much to everybody.